Hi, welcome back. We're going to talk about some stuff with the derivatives today. We're going to have a little bit of fun. All right, so for the first question, this is a warm-up I like to give my students here, see if they remember anything about the derivatives. So the first question says, given that we have this f of 3 is negative 2 and f prime of 3 is 1/2, we want to write the equation of a tangent line. So we got to remember, well, what are the things we need for a tangent line? Well, any line is very simple. We need a point and we need the slope. Isn't that dope? So to get the point, it's pretty simple. I can look right here. This f of 3 equals negative 2. That's the value of my function. So I know my point is going to have an x value of 3 and a y value of negative 2. That's f of x. That's your slope. That's your value, I mean. To get the slope, well, we know that comes from our derivative. We should remember that the derivative is a slope finder for us. So we know that the slope is the value f prime of 3, which is 1/2. So we know our slope is just 1/2. When we want to write the equation of our tangent line, we're going to use our point slope form. Y minus y1 equals mx minus x1. Don't ever use anything else. Don't use like that slope intercept form. That sometimes takes a little bit longer to solve those, especially when we get to uglier derivatives and numbers. This is going to be simple. We're going to get y plus 2 equals 1/2 x minus 3 right there. Very simple, quick way to see if my students remember that, or if you remember everything right there. The next one, we're going to talk about differentiability, and that's what this asks. Does this graph have a derivative at x equals 2? This is that idea of what we call differentiability. And you may recall from a previous video, or even from your calculus courses, to get differentiability, you need to make sure that 1, the function is continuous, and 2, that the derivative exists. And we're going to talk a lot about that today too. But the first one, continuity. So we have to prove continuity. And this shouldn't be too hard. You can almost do it in your head. If I plug 2 in for both of these, I'm going to get 3. So I pretty much know it's going to be continuous, but we got to show our work anyways. So step 1, we have to show that the value exists at 2. And I'm just going to plug that into the bottom function because that's where my equal to is. 2 times 2 minus 1, I get 3. Checking the limit, we're going to take the left and the right. This is a piecewise function, so we want to get the left and the right. On the left, we're approaching the top. That's this x squared minus 1. On the right, we're approaching the bottom function, 2x minus 1. Plugging in the 2's, we get 3 equals 3. So yeah, the limit as x approaches 2 of our function is 3. Now remember, I already knew what the answer was. I could do that in my head. We're just justifying it because that's what we need to be able to show our work. So we can say now that the function is continuous at x equals 3, and that is because the value, whoops, not 3, 2, because the value at 2 is equal to the limit as x approaches 2 of our function. Now the next part is a little bit more tricky, differentiability. We want to check to see if the slope exists. And you might be thinking, Mr. Warner, but we're looking for the derivative, we're looking at the slope. Well, aren't they kind of the same thing? Well, they are. You might be thinking, why don't we just go straight to this step? Well, we got to remember, we have to make sure that it is continuous. Really, that you got to make sure that there's a value there and that we're approaching there. Because you always want to check continuity. For example, what if I have a function like this? Let's say here the slope was 3, and coming out, the slope was also 3. Well, if you just checked that the slope exists, the left and the right side, you would notice that they would be the same value. But then you would think, okay, the slope exists, so it's differentiable. But we know it's not differentiable because there's a jump discontinuity here. So you got to be really careful with that. So checking if the slope exists, what we're really going to look for is the slope on the left, and we want to see if that's equal to the slope on the right. We are going to use the alternate form of the derivative. You might remember that as x approaches c, f of x minus f of c all over x minus c. So let's go ahead and set this up, checking on the left, the limit as x approaches, we're approaching 2 on the left. We're going to use an alternate form, so we can get this x squared minus 1 minus the value at 2, we already know that's 3. We already got that over here, over x minus 2. Same thing on the right. Notice I set this up kind of the same way I do my limits, right? On the right side, we're going to get this 2x minus 1 minus the function minus the value of 2, 3 again, all over x minus 2. Now, you might notice some algebra here. This just becomes x minus 4. This becomes 2x minus 4. So I can do a little bit of algebra here and go x approaches 2 from the left. This becomes x plus 2, x minus 2 over x minus 2. Those are going to cancel. The limit as x approaches 2 on the right side, we get 2. We can factor out the x over x minus 2. Those cancel. And when we sub in, we're going to get 4 equals 2. All right, so let's talk about what this actually means for us right now. You might recall from an earlier video, I talked about something called slope in, slope out. And so let's take a look here. At x equals 2, what's happening here? As we approach from the left side, the slope here is 4. But on the left side, as we leave, the slope is 2. Now, you might recall when we talk about differentiability, the function has to have what we call linear. It has to become basically a line right there. So what happens in this case right here, we don't get a line. We call that, remember, local linearity. Oh, I forgot it for a second there. Sorry about that. We call that local linearity, which means at x equals 2, I should get a straight line. Now notice, I don't get a straight line here. So we say this is not a smooth function. Now what does that mean in terms of the answer? Well, it tells me that the derivative at 2 does not exist. Or we can say, and f of 2 is not differentiable. So we might as well check differentiable. So because they're not the same, the function is not differentiable. Now, let's say instead of 4 equals 2, let's say we got 4 equal to 4. Well, what would this mean? Well, at x equals 2, the slope coming in is 4, and the slope going out is 4. This becomes a straight line. Therefore, we have that local linearity right there. Easy peasy. So this one, we would say f prime of 2 does exist. Matter of fact, we would say f prime of 2 would equal 4 in this case. Over here, it does not equal anything. All right, so let's take a quick look right over here, down here, just get some practice. We saw these earlier. These all were given the following derivatives. We want to find the function and the x value. Anytime you see, they're saying that's the x value right there, by the way. And we're looking for the OG, the original function right here. Okay, so let's take a look here and try these. So for the first one, what we're really looking at right here, this is our remember, this is our definition. So it's the limit as h goes to 0, f of x plus h minus f of x over h. You might recall me saying, ignore this one. Pay attention here. Pay attention to the first part. It's the function of x. And if I circle the same part over here, I recognize that my function is going to be the sign. But be very careful. Okay, that doesn't mean anything because remember h is going to become 0 anyways. But be careful. We want this to be a function of x. That has a pi over 2, so I'm going to call it x. Now, the pi over 2 does mean something. That is what we're letting x equal to. So we're going to say c is pi over 2. Now, some people will say this. Could we let f of x equal sine of x over 2 and let c equal pi? That would work as well. Okay, that would work as well. Very creative if you do it that way. All right, for question 2 here, this right here is our, hiccuped. This is our alternate form. So remember, our alternate form is x approaches c, f of x minus f of c all over x minus c. Don't ever miss this. Don't miss this one. Look at the like part. There's f of x. So f of x is x cubed. C, oh look, there's c, is just 3. Don't ever miss that one, okay? Now later on, we're going to be taking the derivatives of these, so we're going to see this again throughout the year. All right, so going to part 2, we're going to talk about like a toy problem, like how we can read a graph in terms of slope. So take a look at that if you can, okay? All right, bye-bye.